Alrighty, folks, today we are going to talk about groundwater. And this is part of a bigger picture that encompasses surface water. And as you'll come to see, even glaciers. All right. We only have so much water on the planet. Depending on the semester, we talk about how we got that water. As a reminder, or in case I use this in a semester when we didn't talk about that, we talked about how there was a period of time when we were had a lot of volcanic activity, and we were bombarded by a lot more comets than we currently are. And it was a mixture of those two processes that gave us the water that we have today. Now, I always do emphasize that the volcanics activity, outgassing was the vocabulary word for that, is the primary source of the Earth's water. Right? But cannot deny the fact that a bunch of comets smashed into us and they contributed water in that manner as well. So that was our water. We got it a long time ago, and we still have it. We just keep reusing it and reusing it and reusing it over and over again, which is great. It's good to recycle. That's also a great reason to treat it nicely, treat it kindly if you can. If you pay attention to such things, this water cycle, hydrologic cycle, is going to make a whole lot of sense to you. You hear about all the people that are going to be having water problems in India, for example, because the Himalayas aren't getting as much snow as they used to. All right, they depend on that snow melt for drinking water throughout the rest of the year, and so on and so forth. Well, that extra water goes somewhere. Okay, you hear about the glaciers and how scientists are worried that the ice caps in the glaciers are melting. That water goes somewhere. Doesn't just go away. So we have a finite source of water, and we just keep using it over and over and over again. That process is called the hydrologic cycle. Again, you're probably familiar with it as something called the water cycle. We're in college now, so we're going to use the big fancy word. Hydro, of course, isn't very fancy. Means water. Logos, you've seen over and over again. Biology, geology, psychology, that ology. Okay, this is connected to that. That logic, all right? Logic. It's a study of it. It's a thought process. So this is studying the water cycle. All the word means. So it's a circle, it's a cycle. There is no beginning, there is no end, but there is a very logical place to start, and that logical place is, of course, the oceans, because we are covered nearly 3/4 of the planet in them. Now, that's not water we necessarily like, for lack of a better word, because you can't drink it, right? Desalinization is possible, but it's very energy intensive on large scale, very expensive on large scale. Many societies do on a small scale just evaporate water out, recondense it. That cleans it, okay? Gets the salt out of it. But on a large scale, to do like a city or something like that, very expensive. So that's not fresh, usable water. You'll see some numbers a little later, I think, about that. But it is the largest source of water on the planet. So, what the water cycle has us do is the energy from the sun causes a phase change from liquid to gas, which we call evaporation. This is actually a good chunk of questions on your test. All these phase changes, all these ations, as I say. Evaporation, condensation, transpiration, precipitation, percolation. All right, so just, if you don't already know what these words mean, don't forget that they'll be on the test. So evaporation was what phase change I just said? Awesome. Glad you're all listening. Liquid to gas.
Evaporation.
Yes, sir. Evaporation. Liquid to gas. Caused by the sun's energy. Warming it up. You boil a kettle of water. It's evaporating away. All right. Once that water, what do we call gaseous water? Water vapor. We're going to go with water vapor. Goes up into the atmosphere, because it does that when you evaporate it. It gets cold again. And it turns from a gas either into liquid or the solid form of water, which we call ice. The majority of the time it goes to water and then ice if it's going to freeze. There's some weird cases where it evaporates straight to, or not evaporate. It changes form back into straight to ice, but we're going to stick with the model here. So the process of going from gas to a liquid is called condensation. All right. So that's the first big new thing for a lot of you guys, is that clouds are not made of water vapor. A lot of you walk in the door here thinking that. Clouds are made up of teeny tiny little water droplets. And if they're high enough, they're made up of ice crystals. But again, for today's conversation, they're made up of water droplets. So condensation continues. The water droplets get big enough, attached to more and more water vapor, water droplets, and all of a sudden, you've got this thing we know and love as a cloud. And there's a few of them, right? We don't generally like a huge blanket of them across the sky. But little white puffy clouds we formed through condensation of evaporated water. All right. Now we're going to move that cloud over land. And what's going to happen is at some point those water droplets are going to get so big that they can no longer be supported by the cloud. They're more attracted to the Earth's gravity than they are to the cloud itself. So the cloud begins to tear itself apart. Very, very sad. And we call that precipitation, or rain in this case. Now, you know as well as I do, if it's very, very cold out, something could happen to that rain. Might turn into snow, might turn into ice. This isn't a weather class, so we're not going that route. We just need to move the water around the planet right now. So that water falls to the surface of the Earth, and it has one of two choices. It can stay at the surface as something we call runoff. You think of streams and lakes. Or it can percolate into the ground, fill up the ground, and you're ready for the ground word again, and make what we call groundwater. So again, the precipitation that falls to the earth that we just took out of the ocean, turned into a cloud, brought it over the land, and is now raining down upon it, is going to do one or two things. It's going to stay at the surface as streams and lakes, what we call runoff, or it's going to percolate into the ground and turn itself into groundwater. And those are the two different conversations we need to have, two different chapters in your book. Now, whether or not it stays at the surface or goes into the ground, gravity still rules. It will move to the lowest point that it can, which arguably is back to the oceans. Now, if you're in the middle of Nebraska, yeah, probably not headed to the oceans. But again, conversationally speaking here, okay, it's going right back to where it came from. Water will always flow downhill, and downhill eventually everywhere is the oceans. But you get stuck in these little microcycles, okay? Again, if you're in the middle of a continent, not just Nebraska, you could be in the middle of Europe or wherever. Africa, South America, it doesn't matter. But it could arguably work its way back to the oceans eventually. where the sun can warm it up, it evaporates, turns into water vapor, rises up into the sky, condenses back into liquid water, forms clouds. Those clouds fall as rain. Again, it could rain in the middle of the ocean. It doesn't have to rain over a continent. We just needed this, as they say, for educational purposes. We needed to discuss it that way. Any questions on the basic version of the water cycle? You've been hearing it since 3rd grade, I hope. But again, we're throwing some bigger words in it now, possibly. Okay. I left one word out that is on this thing, and it's called transpiration. It's right over that tree there. There's a special kind of evaporation that green plant material does, and it's called transpiration. You sometimes see the word evapo put in front of it. Some textbooks have it, some don't. It is essentially redundant to say evapotranspiration, since transpiration is a special kind of evaporation. So we've mostly dropped that word. Those of you that had biology recently, what are those tiny little holes on the leaves that open and close so it could do photosynthesis? It's not spiracles, I don't think. It's something, though. Stoma? Well, if you've had bio, you remember photosynthesis. And in order for leaves to do photosynthesis, even blades of grass, not just leaves, but anything green, all right, they need to open and close these tiny little holes on them to let the CO2 in and the oxygen out. Well, a lot of water vapor escapes as well. So much so that they made a vocabulary word for it. Okay? The water vapor leaving vegetative material is part of the water cycle. So much so, again, that when you take down a forest, yet another reason deforestation isn't great. Okay? You can mess up the water cycle too. Not just your absorbers of carbon dioxide and releasing all the carbon dioxide, because what do they usually do with those forests? They burn them. Sometimes they harvest them for lumber, not always. But mostly we tear them down to grow corn. Transpiration. Now, there's one part of the water cycle that's not on here. Can anybody remind us what it is? I started our conversation, possibly before the recorder was on, but I started our conversation by talking about this. Where else do we have large amounts of water on this planet? Atmosphere, the oceans, and ice, okay? Our ice caps at the poles and our glaciers in the mountains. That is another very large source of water on this planet. And again, we have a fixed amount. So if it's not in the ice caps, it's not in the glaciers, where's it going to go? It's going to go, more than likely, to the oceans. Sea level rise is real. Sea level fall is also real, but we're not in that mode right now. We're in the everything is melting mode. It's cyclic. It's been going on forever. We are sort of just stoking the fire. It is a natural process. But we've got the bellows out and we're squeezing as fast as we can. So again, ice, while not on this diagram, is also part of the hydrologic or water cycle. Again, any questions before we move on? Okay. So today, we're going to talk about the water that percolates into the ground, making this, and for once be happy, we don't have a big complicated word for it, groundwater. So geologists love to put those bucket wells in all their drawings. When's the last time you saw one of those? All right. I think they closed most of them up in the 90s when I think, what was the movie, The Ring? And that creepy little girl come crawling out of that well, which has since been a staple in horror movies now. But yeah, so we like to show these kinds of wells, and they're much more interesting to look at, I suppose, than the kind with pumps on them. But not a whole lot of these left. But you've seen them in movies. So we've got our well here. We've got some rain going on. We've got a tree. And then you got brown rock and blue rock. All right. We're going to talk about the blue rock first, because the blue rock is, guess what, where the water is. Now it starts up top, of course, and it percolates down. That is an official vocabulary word here. You can say trickle, all right, but we want to use percolate. And what happens is it works its way down through the soil and the rock and whatnot. This is why paving is another big thing that people love to grumble about. All right, development upstream is one of the issues that has caused Sequoia Creek so many problems in the last several decades. All right, the more you pave and put cement over stuff, the less area there is for percolation, or water stays at the surface. When it had spent the last millions of years percolating into the ground. You throw blacktop on it, it can't go into the ground. Not to go off on a rant, but that's what they're talking about. So it works its way through there, and we get the ground filling up with water. Because of gravity, again, it goes down as far as it can. We'll talk a little bit later why it might actually stop at some point and fill up from there, kind of like a sink or a bathtub. So we want to look at that first vocabulary word there on the bottom right called saturated zone. Saturated zone. And the saturated zone is illustrated by that little expando block on the left, where you see those brown pebbles and blue in between the pebbles. All right. What that's showing you is that all of the pore space in that body of rock or sediment is filled up with water. That's why it's saturated. There is pore space in almost every kind of rock that is sedimentary. Igneous, not so much. Metamorphic, not so much. You will find people in certain areas of the world where they get their groundwater out of igneous rocks. It's good and it's bad. We'll talk about that. But 99% of the time when we're showing you diagrams and we're talking about groundwater, I want you to think sedimentary rocks, because those are the sandstones and stuff that have plenty of little spaces in between those sand grains. You can't see them sitting there in the lab room, but they are there. So above the saturated zone, we have the unsaturated zone. There is a word there called vadose zone, but I do not use that word. Why make another complicated vocabulary word when you could simply put the word un in front of a word we already have and convey the same message? So you guys have the saturated zone and the unsaturated zone. Look to the little expando block on the upper left side, and you see that you have the pebbles with a little bit of blue and then the white. That white is supposed to represent air or gas in quotes. In other words, the pore space is not entirely saturated. You follow? It's fairly straightforward, but so if you were digging a well, where would you want to make sure your well goes into? The saturated zone or the unsaturated zone? Saturated zone, because you want to make sure you always have water, right? All right, as you see, that well goes down well into the saturated zone. We've got one thing left to talk about on here, and that is the water table. The water table is actually a surface. That's why they call it a table. Imagine it going into the screen here. And what it marks is the uppermost portion of the saturated zone. It is the plane, the boundary, the whatever you want to call it. It's the last time that that the pore space is fully saturated. You guys tell me, is that a steady, constant thing, or does that move? Yeah, it moves. What kind of things can move the water table? Rain or lack thereof, right?
Erosion.
What would erosion do?
Move material from the top, and then technically that would mean the water.
It'd be a little closer to the surface. All right, so you could erase a bunch of that unsaturated zone, and the water table would be closer to the surface, but it really doesn't move it doesn't affect the saturated zone. That's true, but not horribly helpful. Let's go back to precipitation. So if we have a whole lot of rain, what's the water table going to do? It's going to go up. If we don't have a whole lot of rain, down. Beautiful. Very simple again. What's something else that we can do that's not related to precipitation that could seriously lower the water table?
Temperature.
Not related to weather. I know I said rain, but I'll modify it now. Not related to weather. Yeah, you could start using a whole heck of a lot more. Okay, generally we call it development. All right, you could start using more than is going into it. All right, when output overtakes discharge is the word I want to use here. Recharge. There we go. When discharge is greater than recharge, it's a good way to say it. Your net, of course, effect is to lower the water table. So that actually happened when you guys are too young to remember this. It happened about 20-some years ago when we first moved here. Nirvana bought an old sheep farm up north. And the water company, not the band. And they started bottling water. I used to love Nirvana water. They made really good water. And every time you take a sip, you say, sheep. Because, that was an old farmland, okay? But here's the problem. All the folks who lived around them, this groundwater is regional, okay? It's not just under your house and under your neighbor's house, and you guys, there's a little line in between it, and you've got your water and they got their water. No, it's all connected, right? The ground doesn't have these dividers in it. So they started for business pumping out water where the farmer, for however many years it had been there, had only used X amounts of water. Well, they're bottling the stuff, shipping it across the country, at least regionally, and that dropped the water table a lot. And an awful lot of people whose wells used to be in the saturated zone were no longer in the saturated zone. So it could certainly have an effect. So the water table can move. The saturated zone can be lesser, can be greater. Okay? And we're talking about percolation to recharge it here. That's a word I threw in there, recharge. Questions? Don't worry about capillary fringe. That's what Bounty paper towel does. We don't need to get into this. It's not a hydrology class. And don't worry about vadose zone. We called it unsaturated zone. Okay. Oh, there we go. There's a little recap for you. So in the saturated zone, you only have water in the pore spaces, whereas in the unsaturated zone, you've got air and water in the pore spaces. And as we told you, the water table marks the top of the saturated zone, and that is not fixed. It can move. Okay, now new words, probably for you. Porosity and permeability. Porosity and permeability. These are words we use to describe the saturated zone, or rocks in general. A word we haven't introduced yet, I apologize, but these are words we use to describe an aquifer, okay? And that's AQU, if you want to spell it out for some reason. An aquifer is that body of rock or sediment that we are. This kid wanders the hallways every day, talking to himself very loudly. I have to assume he's got headphones in and I just can't see him. Anywho, literally the day last week when you guys were taking your test, he came through 12 times. Is it singing? It's sort of melodic-ish, but I don't know. That's why I think he has headphones in. Anyhow, for you folks at home, there's a kid wandering the hallways singing to himself loudly. Every day we have lecture. So aquifer is that body of rock or sediment that you want to get water out of. Okay, you're running a town, you bought a farm, you want to dig a well, whatever the reason, and you guys are depending on water coming from the ground. You don't have a stream or a reservoir nearby to tap into. You're concerned about these two things. Okay? So the first one is pore space. The pore space is simply a measure of the amount of holes in that rock. Remember we talked about well, I think I used the word pore space actually a couple minutes ago. All right, those spaces in between the little grains that you're either going to fill up with water or air. Remember those? It's just how much is there. So you have to pick, like, imagine a 1 foot by 1 foot cube of that rock, okay? And of that 1 foot by 1 foot cube, how much of it is sediment and how much of it is pore space? What do you think you want? A lot of pore space or a little bit of pore space if you want to be able to get water out of that rock?
A lot.
A lot of pore space because you can put more water in it, right? It has the potential to hold more. Now, if you're not following me here, think about that sponge sitting on your kitchen counter. All right? You got spongy material and you got holes where the sponge isn't. I've never checked the porosity of a sponge, but let's just say that that is 60% spongy material and 40% holes. If you can measure such a thing, you can, but you would say that that has a porosity of 40%. It's a measure of the holes, okay? So you have to pick a volume of rock to look at, and of that volume, how much of it is holes, how much of it is rocks. We're concerned with the holes. And as you guys correctly guessed, the higher the amount of holes, generally speaking, the better. You don't want so many holes that it collapses, of course, but... All right, so that's important. You want to be able to hold a lot of water. But what's almost more important is this next word, permeability. You've heard the word permeable before, all right? It means you can get through, right? Permeability is a measure of the interconnectedness, big word, of the pore spaces. So, yeah, you can actually have holes that aren't connected. I like to give you the example of a big old hunk of Swiss cheese. Again, I grew up watching Tom and Jerry and Bugs Bunny and all that stuff, and for some reason, they were always holding up a big old hunk of Swiss cheese when there was a mouse involved. I've never actually seen a mouse eat cheese, but cartoons led me to believe that was true. So go back to that sponge for a minute. You stick that sponge under your kitchen sink, and you slowly turn on some water. It's going to fill up with water, and guess what? It's going to start trickling through the sponge at some point because that water moved all the way through the sponge. However, if you stick that wedge of Swiss cheese underneath the kitchen sink, what's going to happen? The water's going to fill up those couple of holes at the top, right, and it's just going to spill all over. Why? Because those holes don't go all the way through. Sure, there's holes in the middle and on the side and so on and so forth, but they're not connected to each other very well. You follow? That's what permeability measures. I like to call it flow-through-ability. It's a made-up word. Spell it however you want. Hyphenate it. I don't care. All right. How well can that water flow through the rock? So now we're seeing that it's not just about having a bunch of holes to put your water in, but dang it, all those holes need to be connected. So you need both a good porosity and a good permeability in order to be a good aquifer. You follow? All right. we not letting me click? Have to get off my arse here and see. All right, here's a list of common porosities and permeabilities I'd like you to memorize. No. No. But we are going to make some generalizations. What did I tell you a few minutes ago? Make good aquifers. I said when we're talking about all this stuff, picture what kind of rocks? Igneous, sedimentary, metamorphic. You started to say it. Sedimentary. All right. So generally speaking, sedimentary have the best porosities and best permeabilities. They have the most holes. This is also not just about rock, but soil sediment. Okay. On top of most rock, you know you got a whole bunch of dirt. So this will go through and tell you all your porosities and permeabilities for sediment as well. And I'm sure you can imagine not sediment that's not glued together has better porosity and permeability than sediment that is glued together because you got that stupid glue in the way. So sediment, generally speaking, has a higher rate than the rock itself does. We also told you that igneous and metamorphic, not so great. They show up as crystalline here. All right. And you see even down to zeros for porosity. The exception in sedimentary is shale. Shale loves water. It's what we call hydrophilic. You might not know the suffix philic, but you know its opposite. Everyone knows phobic, right? Phobic is you're scared of. All right. Philic is love. Audiophile, someone who loves music. Okay, whatever file, you put that word in something in front of it, it means you love it. I can think of another one, but it's not a good one to say out loud. Anywho, so philic is like. So shale is hydrophilic. More so, clay is hydrophilic, and that's what shale's made out of a lot of times. So what happens is shale will suck in a whole lot of water, but it does not like to get rid of it. It holds on to it. And I mentioned a little while ago that we're going to have at the bottom of all these aquifers some sort of layer that stops everything, and we fill up from there. It's sort of the Tupperware bottom, if you would. Okay? That's usually in our diagrams a layer of shale. It could easily be igneous rock or any other such thing. But we usually talk about in terms of shale in this class. So shale is going to be the bottom to our aquifer, and as you'll see, sometimes it's a lid as well. So again, don't worry about these numbers. Just remember that generally speaking, sedimentary rocks make the best aquifers. Asterisk on shale. Now, one last thing before we leave here, the igneous rocks. You are bound to, especially living in this part of the country, run into somebody from Vermont or New Hampshire, Maine, that will go on and on and on about the water from their granitic aquifer. Granite aquifer. You say, but I learned in geology class that granite isn't porous and especially isn't permeable. How do you get water out? Well, they're not lying. Okay, there is. But here's the deal. It has to be cracked. Rocks are old. They're cracked. There's no question about that. All right. So what happens in that case is that they're on a bed of granite, a body of granite, that has some giant old cracks in it. And just like everywhere else on the planet, water trickles into it, percolates. I'm using the right word there. Percolates down into it, gathers over the years, and they've got a source of water. Only problem with that is, well, let's go back to why they love it. They love it because it's really hard to dissolve granite. All right? So it is, for all intents and purposes, just pure water. Let's go back to some stuff that you know about. We've kind of touched on here and there. water dissolves all kinds of things, right? You put water in limestone, you end up with calcite. We call that hard water. You run water through sandstone. A lot of times it picks up iron. That's iron in the water. You may have been somewhere where they had egg water, sulfur water. All right. When water flows through sedimentary rocks, yes, it does pick up stuff, but it's also a hell of a filter. Again, some of you may know this, some of you may not. One of the best filters to have for your swimming pool is a sand filter. Okay? Sand is an amazing filter. So yeah, you might dissolve a few things here and there, and we've got ways of treating it to fix some things here. But overall, it's a win-win situation. The problem with the granite, first of all, if they're on well water, more than likely they don't have sewers, so they're on septic as well. And most folks this day and age are smart enough to put their septic downhill from their wells, but not everybody. And there could be somebody living up the hill from you as well. And there's no filter when you're just pulling out of a granite aquifer. So, yes, it's crystal clear, beautiful water, as long as there's not an old gas station next door, or an old this, or an old that. Okay? But yeah, you will at some point in your life, if you ever find yourself having a conversation about water with somebody, which you might, you're bound to hear about their granitic aquifer. So, all right. And there finally is that word aquifer. We've used it a dozen times by now. Again, it's a body of rock or sediment that yields water. Gives up, yields. It implies it has both a good porosity and a good permeability. You got it? And I switch. So your book will go on to talk about other aquifers. And we're going to acknowledge the terms because they're real things. But they're not aquifers. If an aquifer yields significant amounts of water, going on to talk about things that don't yield significant amounts of water, well, they're not really aquifers. Anyhow, that's just me nitpicking. So the first one is aquitard. All right? What does the word retard mean?
To repel or
to slow down. To slow down. All right? So an aquitard is a body of rock or sediment that yields water very slowly. It gives out water not real well. Okay? There's water there, but it's really a pain in the butt to get it out. That's typically due to a low permeability. Picture getting that fresh, thick shake over the summer sometimes, and you go into that straw and you go, and nothing's coming. You get like one little bit, and then nothing. That's like an aquitard. Okay? An aquiclude, this is really big in the definition here, a layer of rock or sediment that yields little to no water. Well, then why the hell are we talking about it under aquifers? Because this is that shale. All right? This is that rock that is in your aquifer, but hopefully you're using it as some sort of capstone. Either at the bottom of everything, or as I said earlier, you'll see it, maybe it shows up at the top as a lid. Very low permeability and possibly just low porosity as well. There's not a whole lot of water there, and it's really hard to get out. Aquiclude. Exclude. So you will see aquitard and aquiclude when you read this chapter, which I always encourage you to do. But we want to focus mostly on aquifer, because that's what we want. That is a body of rock or sediment that you can get decent amounts of water on an everyday basis. Okay. Within the realm of aquifers, those bodies of rock or sediment which do yield significant amounts of water on a daily basis, we have two kinds that we talk about, a confined and an unconfined. We have essentially been talking about unconfined this entire time. Remember I told you that it rains at the surface, that water percolates down through and fills up from the bottom up this body of rock or sediment that we're going to tap into, right? It's unconfined because it doesn't have a lid on it. Hang with me, you'll see the lid in a minute. As you can imagine, as long as it's raining, or it's melting snow, or whatevering, it's very easy to recharge one of these, because it just has to trickle through. On the other hand, this confined aquifer, I should say, it has that lid that I've mentioned a couple times with shale. You're going to see a picture in a moment. So not only does it have a bottom, but it has a top. And that top makes it difficult for the water to get in. Obviously it's getting in because there is water there, but it is limited. So confined aquifer has a lid, if you would. Unconfined aquifer does not. Let's show you a picture so you can see what I'm talking about. We're going to ignore those black discs for the moment. This is an unconfined aquifer because there is no... Why don't I just show you a confined first? I really don't know why we do this way. Because there is no boundary up at the top. Okay? Ignoring those two black tire track looking things for a moment. Speaking of which, since we're getting near the end, that brown rock with the speckles on it is what rock symbol? Dirt? No, it is rock. So the dots, pencil dots, speckles here, that's sandstone. Okay? What's the tire? Limestone is bricks. What are the tire track, the dashed things? Helped by making them black in this picture. There's your shale. Okay? There's your shale. So, unconfined aquifer, you got to drill a well in there. You want to make sure you go past your water table, as we mentioned before. By the way, that's public record. Okay? If you're ever, or your folks are ever in the market, you buy some land up north or whatever, and you want to drill a well. Not everyone has the same scruples as everyone else. Make sure your well driller drills your well at least as deep as all the folks around you, which again, you simply need to go into town, ask them to see the records or what the average well depth is, because most folks like me will hire the cheapest person out there. And the cheapest person may not know what they're doing. They may do that first well that we see on the left-hand side, and they say, oh, we hit water, Mr. G, you're good, we hit water for a good, it's hard to tell scale here, but we hit water for a good 50 feet, you should be great. Or my neighbor down the road, his well goes down 400 feet. Guess who's going to run out first? All right, so more vocabulary words. Perched water table. Big one up at the top there. Perched, as in a bird sits on a perch. All right, that's these lenses of shale that are catching water. Remember we said shale is an impermeable membrane. It's an impermeable layer. Water will build up on top of it, giving you a false water table. That's a much better word than a perched water table. But the book that I took this from, whatever semester I made this lecture, used the word perched water table. It has water now. It might have rained recently. Might have just had a snow melt. Plenty of water there now, but you put your well into there. After a while, it's gone. The other word on this that's important is the word spring. When we talk about streams in geology, we have one word, whether it's a lake, a river, a creek, we call them all streams. Because in reality, what we mean when we use all those different words is the size of it usually. All right, and we're not really concerned with how wide and deep a river is usually. So we get rid of all those words and we just talk about a stream. One exception to that rule is a spring. A spring is groundwater leaking out at the surface. In this case, we conveniently have intersected one of our lenses of shale that catches water, that trickles through, and that leaks out because of the side of the hill here. A wonderful example, and I don't know after 20 years why I don't have pictures, probably because I'm always driving, but when you go down the thruway and you hit Little Falls where all the shale's out, and you see those really awesome blue ice flows, okay? Each one of those is at a shale layer. If you happen to be driving by after a heavy rain in the summer or spring, and you do see the little waterfalls leaking out, those are at shale layers, okay? But they're most magnificent in the wintertime when they get that whitish blue look to them. So awesome. So that's groundwater that seeps through, hits the layer of shale, runs along to the edge, because it happens to be sloped down there, and flows out and freezes and makes those really cool flows. All right, just to recap, I started by talking about that this really shows us an unconfined aquifer because while you can't see the bottom layer that's capping this, that's holding all this water in here, you can see the top. And you see that there is not a lid on here. All right? Yeah, there's a little bit of shale here and there, but generally speaking, the water can percolate down through and fill up that water table quite easily. We introduced the idea of false water tables or perched water tables, and we mentioned that if that should happen to coincide with the lay of the land so that it can leak out at the surface, we have a special word for that called a spring. And so if you buy spring water, it darn well better have leaked out of the ground instead of flowed through a ditch, all right? Or as more and more of these water companies are doing, just filtering municipal water. Nestle's famous for that one. I forget if it comes from St. Louis or somewhere. It says on the bottle usually. A confined aquifer, on the other hand, please ignore the giant word artesian well for the moment. A confined aquifer has a capstone, a lid, as I've been saying. What did we say the dashed rock is? Shale. So this one has shale on the top and on the bottom. And what that basically means, at least in this diagram, that the only area that you could fill up that aquifer at is up at the very, very top where the sandstone is sticking out at the surface. If it runs in on the shale, it might absorb into the shale, it might work its way into the sandstone. But if it hits that top shale, it's just running down the hill. So confined aquifers are much harder to recharge or to refill because you, generally speaking, have a more limited area that you could fill them up in. They do, however, have one really neat feature. It's called an artesian well.
Cheese.
Yeah. Not artisanal. You say cheese?
Yeah.
Yeah. And it's artisanal. It's different than artesian. I believe it's an area in France. I remember from like a gajillion years ago looking it up. So that capstone puts this system under pressure. Even though it's not a pipe, because if you go into the board, there's not like shale behind it as well to make like a third wall, if you would. But just the simple presence of a top and a bottom exerts pressure on that sandstone in the middle. And it pressurizes the water. So not only do you have the downward slope due to gravity, but if you poked a hole in that at the very bottom, it would shoot out like a drinking fountain. Or like one of those stereotypical oil wells you see in the old black and white cowboy movies, where everybody's dancing around as they struck oil. So, confined aquifers are pressurized, and that allows you to have a pressurized well. This is why we simulate this with water towers. You know why water towers are up in the air? To provide water pressure. All right? And that's exactly what you're doing here. There's a neat little experiment you can do. This is what that red line is all about there. In hydrogeology, which is the study of groundwater, typically, we've got some wonderful words for it. We call it head. All right? And you've got head 1 and you've got head 2. Head 1 is at the top of your hill. Head 2 is at the bottom of your hill. And you're looking at the pressure difference. And they will say wonderful things like, that is good head and that is bad head. And we try not to giggle at each other. But those are the words they chose a couple hundred years ago. Or at least 100 years ago. So here's the neat parlor trick. If you ever want to earn $5 in a bet. You need some fairly simple things that are sadly often available at a party. You need a length of rubber tubing. And you need a funnel. And you need some liquid. So you very slowly but surely, you need a friend for this as well, fill up that tube with the liquid. You have your hand on one side, thumb at the top of the tube, and you've got the other hand with the funnel, right? And so you fill it up with some root beer, something like that. And once you get it all filled up, you have to take your thumb off every so often so you can fill up the tube too. Once you have it all filled up, you hold it up into the air. I would go outside if you're using root beer, it's very sticky. And you take your thumb off, but first, you bet the person that when you take your thumb off, the water, or the root beer in this case, will shoot up as high as the funnel. Head wants to equalize itself. The pressure will equalize itself. That fountain should shoot up as high as the top of the aquifer here. And again, if you do it with a funnel and a tube, it should work as well. Now, back when I was growing up, that was hard to prove because we didn't have cameras with slow time. What's it called?
Slow motion.
Slow motion, thank you. We didn't have cameras with slow motion on it. You guys might actually be able to catch this. Physics says it's true. All right, so let's say you managed to win that bet. Somebody actually captured it with their camera, and you won $5. You say, wait, you want to double your money? Chance of winning your money back or double my money? They're going to say, sure. You say, okay, I'm going to take my thumb off of this, and no root beer is going to come out. How do you do that?
Same height.
No head, exactly.
I sometimes do that with like pool noodles.
Yeah, you might be messing around. Exactly, messing around. And if you've ever had to clean a fish tank, it's also sort of the same idea to get that flow. Or if you've ever siphoned gas, you guys have never done that, I'm sure. But it's the same idea. All right. So again, to double your money back here, all you need to do is have the funnel and the edge of the tube at the same elevation, the same height. And there is no elevation difference. There is no pressure. There is no head. Okay? There you go. So, confined aquifer, pressurized, hard to refill, artesian well, self-flowing. Back here, you either need to get that little bucket that cranks down, or what most people on the planet have is a pump house. Around here, that pump house probably had better be inside, okay? Your well pump should be inside because it can freeze. You move further south, you tend to see little things that look like dog houses if people don't have a dog, but that's where their well pump is. Yes?
How do geysers always?
Geysers is totally different.
It's
And I
from,
wish
like,
we,
heat or
yeah,
something,
it's
right?
boiling. It's literally boiling water. And it's more like a steam kettle in that sense. That is only triggered when the pressure hits a certain level. But yeah, that is hydrothermal. That even has a special word. So that's your body of magma heating up the groundwater. And I've even got a video on that one. But once you've seen like 6 geysers, it gets a little boring. So yeah. All right, we are out of time for today. So we'll pick this up when we get back.